Okay, so let us implement linear regression in a neural network form. And we are going to use PyTorch in our implementation because you already did linear regression in NumPy and other frameworks. So we are going to use this as an excuse to work with PyTorch tensors. However, we are going to do other things mostly from scratch. Okay, so linear regression, as you know, is a model that assumes a linear relationship between the features X and target Y. Like I said, for now, we are assuming scalar Y. This is the form that we are looking at. And the last function is a mean squared error. We already discussed that in the previous lecture. And the gradient will be computed using these equations. And here, let's start with the code. So like I said, we are going to use Torch. And what else we want? We may need some plotting. So let's use matplotlib. We want this to be reproducible. Let's fix the seeding in our generators. Let's make synthetic data. To do that, I'm going to write a function here. So let's just leave this for now. Okay, so we want to basically have the model. So the arguments of the function will be, of course, the weights, the bias, and the number of samples, and basically some form of noise that will be added. And we are going to use just standard Gaussian noise. We want the function to return the feature matrix for us and the target vector, looking at something like this. Okay, so basically we have the weights and we have the biases, the samples, simple, small Gaussian noise. And this will give us the feature and return the features and, of course, the predictions or the target vector. To make things maybe more obvious here, this is really a good practice in coding. Maybe not in Python, it's not critical for Python, but just having the types that we are going to expect this variable to have and determining them here in the function will make it more readable. And later you will see it will make your debugging much easier. So we have bias, samples, and noise. So bias will be good. And like I said, we are expecting this to give us the features and the prediction. The features will be a torch tensor, and the prediction, of course, will be another torch tensor. Okay, note that here it doesn't really recognize this. What does that mean? It means that I haven't defined what's tuple, so I have to import this from the typing. So let's go back here, see everything looks okay for now, and now we can go on writing our function. Okay, as you see, I already have a suggestion here. I'm going to just use this because, again, I assume that you know most of this stuff. So D here is the shape or the length of the weights. You could use just len of weights. Like I said, weights is a vector, so you could do that. But this is more general in the sense that sometimes we have multiple y, and y is not a scalar, it's a vector itself. So we have, like, for example, 2 values for y, not just one scalar. And this is a more general case. So X is the feature matrix, which is basically the value of t features in each one of these samples. And num samples is either the entire data set size or maybe the batch size. Later we will talk about that. And noise here is just randomly generated noise, of course, added for each one of these synthetic data samples. And then this is basically what we get as the ground truth for y. Remember, this is synthetic data. let's go on and write our linear regression. Okay, so let's write it as a class. Okay, so going to just describe what I want to do. And for now, like I said, we are using our manually derived gradients. And with that, let me just write this down. Okay, so just remember in practice, we don't need this one, this two, because later on this will be multiplied by the learning rate. So, okay, so this is the class that we want to write. We need an init method, of course, and let's write that. Needs the input size. Okay, what do we have here? We don't need num feature. We need the learning rate, of course. So let's just write input size, which we have an integer and a learning rate, right? So I already see that here. So, and we have a float, and so let's even make it even the random weights. I want them to be even smaller. And this is learning rate. And like I said, since we don't have autograd, and that's the input size. Okay, so that's that. We have our init method. We could add some print statements maybe later, but for now, let's just go with this. Now, what we want a forward pass, right? We want this to compute the predictions given our current features, right? And this will return our linear computation. Use tab here. That's it. This is our forward pass. Basically computes the values of y, the output of the neural network, right? Okay, what else we want? We want a function that computes loss, right? So let's do that too. Okay, I see the suggestion looks okay to me. I'm gonna use that. And notice that this can be really a static method. I'm not sure if you recall that. So I could just use a static method here with a decorator. But for now, let's just go with this. Now we want to compute our gradient steps. And let's see what we have. Okay, self x. And this gives me, yep, this sounds good. Okay. So let's write this up. I'm gonna just write an error here and make this more explicit, right? So it will be easier for you guys to see. Okay, so that's how we compute the gradients, and we have to compute the step sizes, right? Using this gradient. So we need another function here. Like I said, later we will see that your life will be much easier. So let's do this. We need the x and y, and this will give us the step size, which is a float, right? So let's just write it. So what we need for this one gradient descent update, we need to compute the forward pass, and then compute the loss, and then compute the gradients, and then update the parameters. So these are the steps that we want. Okay, good. So let's write them. So like I said, first, let's do forward, which is y ahead, and 2 loss, and 3 the gradients of weights and biases. So something that I skipped here, maybe I should have explained. So remember that the gradient of the bias is basically the average error. And that's how we ground the error to 0 to move it to the origin, if you remember. Okay, so with that, now we have the gradients, the weights and biases, and we need to use that for our updates, right? Use a more compact notation. So this is it. We update the weights, and this also returns the loss. Okay, this looks good, right? And now next we can go to our stochastic gradient descent, which requires to make mini batches, right? That's the next step. Let's make some mini batches. Okay, so what we need. We need X and Y and some batch size to choose. And like I said, we need to shuffle them, right? Maybe not. Sometimes we don't need to necessarily, but let's keep it as an argument. Okay, so we have X, Y, batch size, and shuffle. Okay, so what does this return? It will return a generator, if you remember. So basically, actually, maybe generator is not the best option. Maybe we can use iterator, right? Generator is more common, and the reason is you have more control. But here, the reason that I'm not writing generator is you have some extra arguments that I would want to talk about them for now. So let's use an iterator. And iterator basically returns the two outputs. This basically yields all of these batches of X's and Y's. And here we have to shuffle them. So if shuffle, we want to keep this torch propagation. If not shuffle, we just stick with what you have. Okay. Now dx basically give the X and Y in each batches. So this is how we are doing this. For start in the range of 0 and n, the step size of batch. Okay, so what will be the end? End will be the start plus the batch size, right? And since sometimes we may hit the button, so we have to use the minimum of that, or last, we just need to enter the range of the batches. So let's just use the indices start to end, right? Okay, so with that, we just need to our generator to yield XP and YP. Okay, good. So this is how we are making the mini patches. And now we can train the model. Okay, let's write this. So it takes in the model, which is the class that we have, X and Y. And we still need to enter the batch size. So model, X, number of epochs, and batch sizes. So we use 32. So let's return some form of average loss across the epochs, which will be a float pretty decent. And this is the training loop. And we are reporting the average loss, right? So in each one of these epochs. So we have the epoch averages. Like I said, it's a list of floats. And for now, it's empty. So for each, okay, so let's see what we have here. For each epoch. So basically, this is the loss that we get in each batch, and the model already took a step using these batches toward a better parameter. So the training is done, but we promised here that we are going to return some average loss per epoch. So let's then add up all of these losses that we are collecting in each epoch. Let's change this name. So this is the total loss per that epoch. And since we are calculating the average on fly, we need to have a counter here. Let's just put a counter here, maybe number of batches. So this is okay, that's it. Now for that epoch, we can compute the average. I'm just scared of this when it starts from 0. Let's just be careful, huh? Doesn't hurt. We don't want to have division by 0. So we can add some verbose messaging here. Training and model, yeah. Oops, so you see that this is not defined, we have to define this too. So verbose is just a Boolean, and let's say default is true. Okay, so what we want to print out, if verbose, we want to print out maybe the model parameter, and I see there are some nice suggestions. But since we wanted to, if you remember, we are synthetic data, we had some ground truth. We can write that out too, and maybe compare it with the ground truth. So let's just add this here. Now we want to make some synthetic data using our function. So let's start with maybe a small two-dimensional weight, so the true weight, and let's just choose two values. Okay. Let's have a true values. Let's generate 1000 sample from this. And then this way we can basically run the generate synthetic data. We have the model, which is a linear. And then we have the input size. Let's just not change the learning rate. And we just need to train it, right? So I want to separate these things out. So let's keep this here. And so, I mean, we really can title this off for now because we are doing it anyways here. Okay, so let's run our happy little code. What's happening here? Currently here the learning rate, which is correctly a tensor of this shape, is multiplying by a 2 by 1000 tensor. This is strange because if you remember, 1000 is the number of total generated samples. And then later we basically work with much smaller batches. So I didn't expect that. There might be an error somewhere that propagated and cascaded here. One thing that you should remember, often when PyTorch is trying to align tensors together, maybe during multiplication or even summation, when we don't explicitly determine like the dimensions, we have to be careful. So let's just take this here. I want to compare it to the error here. So, okay, so what do we expect here? Weight is a column, right? So, and we multiply it by x. X is, of course, 1000 by 2. We expect a 1002 matrix multiplied by a column of size 2. So the answer will be a vector with this size. And then later, when we add this to the bias or noise, which is now 1001, this is where PyTorch must be creative to expand the dimension, not necessarily reduce. So since it doesn't know how is this happening, instead of adding a 1 here, it actually does this, which returns instead of what we expected, right? So we don't want that, to let PyTorch make these decisions for us. So to avoid that, we are going to cast these weights into the form that we know. Basically, whatever is the first dimension, we want the second dimension to be 1. I don't care what's the first dimension. I want this to be 1. Okay, so instead of saying I don't care, put -1. Okay, it's a placeholder. Really, it's not really literally -1. Okay, so let's do this change and go back, see if our life gets any better. Okay, so that's that. And with that, let's run everything again. Something else happened. Oh, yeah, of course. So we came until here. That's great. And the last line cannot print this. Why? Because basically we are saying that this should be fine because the tensor is now least and we can print this, but the tensor here is still a tensor and we are saying that printed in a float. That's not happening. So let's just tell that we want this to be the item or the value of the tensor. Okay, so with that, let's run again. We are good. So later we will do the same code, but with backward and autodiff and more tools instead of writing it from scratch. Okay, so let's plot the training loss, and here I wrote a function for that that basically takes in the model and it plots the loss history, the amount of loss per each one of these batches. So let's make sure we have that. We append all of these loss values here, the steps. So let's do that. So we need a self loss history, right? And I see that we don't have it. It means that we haven't initialized it. So we have to do that first. Let's keep that. And here, self-loss history. And we want to append all of that. And good. And let's train everything again. And now we can plot. And we are plotting the model, right? That's it. And you see that the loss is going down with the training.